Swayam Prabha. Digital India. Educated India.
Hello everyone. So we are continuing our discussion on combustion of solid propellants, and we were continuing the evaluation of burner of composite propellant. We have already somehow introduced the processes involved in combustion of composite propellant. So, we will just quickly look at the various processes involved in the combustion of composite propellant, and then we will try to get a simplified mathematical model to understand the burn rate of composite propellant, and we want to see that how the burn rate of composite propellant is also going to be a strong function of pressure, which we have already seen in case of double base propellant. Now, as we have already seen that the physically the double base propellant is homogeneous, whereas the composite propellant is heterogeneous in nature. So, of course, the burning process is distinctly different than the double base propellant, and that we have already started discussing in the previous lecture. So, today we will try to focus on the evaluation of burn rate of composite propellant, but we need to make sure that we understand the process very carefully, that how the the decomposition of crystalline oxidizer play an important role there, how the ammonium perchlorate premix flame is forming, and what is its role on donating oxygen species, which will in turn going to mix with the fuel species formed from the pyrolysis process, and that will form the premix diffusion flame, and then finally the final products of APPF and the PDF you will mix together and form the final diffusion flame or the secondary diffusion flame or SDF. And the popularly known model to describe this triple flame structure is the BDB model. So, we will continue our discussion by considering that BDB model. So, let us look at how we can evaluate the burn rate of composite propellant. So, I think in the previous lecture we have shown this one, that ammonium perchlorate first will decompose. Once we ignite it, it will decompose, it is going to form the perchloric acid and ammonia, and then later it is going to produce some oxidizing species, some inert products and some oxidizing species. And we also told ourselves that the BDB model is considered to be the well describing model for the burning process of composite propellant, and the model advocates the triple flame structure. Now, the flame formed due to the decomposition of ammonium perchlorate is known as the premix flame, or sometime it is known as the ammonium perchlorate premix flame, because no mixing with other constituent is involved here. Therefore, the first flame appears in the decomposition in the combustion of composite propellant involving perchlorate based oxidizer is the APPF or ammonium perchlorate premix flame. Now, after the ammonium perchlorate premix flame, the oxidizing species will be formed, whereas the binder, which is HTPB, which in turn a fuel as well, because HTPB is simply the hydrocarbon. So, on pyrolysis of this hydrocarbon, it is going to produce the hydrocarbon species or the fuel species that will mix with the oxidizing species evolved from the premix flame, and that will create the primary diffusion flame, which is showing here that O by F flame bar or the diffusion flame. So, mainly we can say that the ammonium perchlorate based composite propellant consisting of one premix flame and two diffusion flame. two diffusion flame. The first one is the primary diffusion flame, and the second one is secondary diffusion flame. And this triple flame structure is advocated by this BDP model that we have already seen there in earlier case. So, we are considering our discussion based on this BDP model. Now, the typical temperature of the APPF flame is around 1300 to 1400 Kelvin that we have already discussed in the previous class. The primary diffusion flame may go temperature around 2800 Kelvin, whereas this one can go 3200 to 3300 Kelvin. Now, we must appreciate, although we are talking about these three different structure of flames, but they are really narrowed in a small region or small thickness above the propellant surface. So, what we are talking about, this is the propellant surface. So, if you look at the structure of the or the morphology of the flame, we can morphology of the propellant surface, they are having scattered ammonium perchlorate of various sizes, like there will be some bigger size crystals or smaller size crystal dispersed on the propellant surface. So, the heterogeneity of the propellant surface is going to definitely play a role in this formation of this type of triple flame structure. So, depending on size of the particles, the pressure involved in the chamber, the flames what we talked about like the premix flame, primary diffusion flame and secondary diffusion flame have different levels of importance. At low pressure, the chemical reactions are slow and it takes long time to complete the combustion. So, therefore, at low pressure we can say the premix flame is the controlling factor or you can say the premix flame dominates the combustion process in the low pressure, because when the pressure is low, the chemical reactions are slow. So, it takes longer period of time to complete the combustion. So, premix flame actually tells us that how the combustion will take place for the composite propellant. So, premix flame is dominant in case of low pressure instances, whereas when the pressure is high enough, the chemical reaction take place at a much faster rate, because large number of molecules will be available. However, the diffusion will be does not occur that faster rate with increase in pressure. As a result of that, the diffusion will control the combustion process in the high pressure. So, in a sense we can say that at low pressure the primary flame controls the combustion process, whereas at high pressures the combustion is controlled by the diffusion or the mixing process, because we know that at high pressure chemical reaction rate is much faster. However, the diffusion process is not improved that way. So, the mixing between the oxidizer species and the fuel species will influence the overall combustion process. Now, in the previous lecture I think we have seen these flame pictures earlier for various ratio of binder to oxidizer crystals, and we have seen that as the fuel species is increasing, the flame color is changing. Now, the purpose of bringing this here just to show you that the thickness what you are talking about, it is really like a very narrow region, about like 0.2 to 0.5 millimeter region where these three flames exist. So, based on the pressure, based on the ammonium perchlorate sizes, and of course, there are other parameters involved which will influence the relative importance of the each of these flames. However, for the sake of simplicity, we can just consider a narrow region of the flame which is going to transfer heat for the pyrolysis and decomposition of the the polymeric fuel and the ammonium perchlorate crystals. So, flame itself we can consider to be a planar region above certain distance of the propellant surface, which is considered to be the standoff distance. Like we can consider these 3 flames at a certain plane, which is located at a distance x star from the propellant surface. So, this is the propellant surface where we have the crystals embedded in the polymeric fuel. So, flame is located at a certain distance from the propellant surface, which is providing the heat to the propellant surface for further decomposition of the ammonium perchlorate crystals as well as the pyrolysis of the polymeric fuel. That is the basic of the combustion process of composite propellants. Now, if we look at the typical thickness of reaction zone as a function of pressure for APHTP based composite propellant, this experiment was conducted at low pressures, but still we can see as the pressure is increasing from 0.02 to 0.03, 0.5 and 0.1. So, basically it is like 1 atmosphere. So, the experiment was conducted from subatmospheric to slightly above atmospheric. One can see that the thickness of the reaction zone is actually decreasing as you increase the pressure. So, therefore, the heat transfer is going to be better as the standoff distance is going to reduce once we increase the pressure. So, basically the pressure has an important role on the overall combustion process of the composite propellant. So, definitely as we have seen in the WFS propellant, in a similar line we can actually say that the burning rate is also going to be a strong function of pressure, but with some simple mathematical relationship we can actually try to see that whether we can represent that burning rate R in terms of strong function of pressure. For doing that, we just need to consider some simple representation of the flame. As I said earlier that just a 3 flame or triple flames are located at a region above the propellant surface at a distance x star, where x star is denoted as the standoff distance. Now, this flame is going to provide the heat for further decomposition of the ammonium perchlorate crystals and the pyrolysis of the fuel binder. So, what essentially it is doing is it is providing the heat to the propellant surface for the further reactions. So, what we need to equate that the amount of heat coming from the flame is going to be used for heating of the propellant as well as the pyrolysis of the fuel binder. So, heating of the propellant means there will be some initial temperature of the propellant that will goes to some surface temperature of the propellant Ts, and once the reactions occurs it will reach to a flame temperature. So, if you just plot the temperature versus x, we may say that the temperature is increasing from the surface temperature Ts to the flame temperature Tf. So, this is the typical temperature profile. So, the temperature increases from the propellant surface temperature Ts to the final flame temperature Tf. Now, if you consider this to be a linear profile, then we can actually try to write down the heat transfer due to the coming from the flame for increasing the temperature of the the propellant surface. We can simply write down that heat transfer to the unit surface area of the propellant from the flame surface. We can write this as minus kg dt dx. Now, if you denote this kg as the thermal conductivity of the gas, thermal conductivity of the gases in the standoff region. So, we are talking about the standoff region here. and if we consider a linear profile of this temperature, we can simply write that the heat transfer per unit surface area of the propellant from the flame surface is equal to minus kg dt dx, which you can write kg Tf minus Ts by x star, where x star is the stand-off distance. Here we have to remember that we have considered the linear temperature profile in the above equation for just the simplicity of the analysis. Now, what exactly is done by taking heat from the flame surface? The heat is going to increase the temperature of the propellant from the initial temperature Ti to the surface temperature Ts, and also it is going to supply energy required to vaporize and pyrolyze HTPB or the polymeric binder and decomposition of AP. So, we can say that some heat is required for endothermic reaction, and heat required to raise propellant temperature. So, whatever the heat transfer is coming from the flame is going to do two things. One is going to provide heat for the endothermic reaction, which is like the pyrolysis of the polymeric binder and the decomposition of ammonium perchlorate crystals, and also it is going to increase the temperature of the propellant from its initial temperature to the surface temperature. So, if you denote that the net rate of heat absorption at the surface and of course, per unit area, we are considering per unit area here. We can simply say that m dot is the rate of vapor released from unit surface area of the propellant, that is denoted as m dot into C is the specific heat of the propellant into Ts minus Ti plus some endothermic heat is required for converting the fuel and the oxidizer to the vapor or the gaseous state. So, let us consider this heat is that as for required for the endothermic reaction, which is delta is V. C is the specific heat of the propellant. So, what we can say here that this heat is coming from the required heat is supplied by the flame. So, we can equate this, that heat input to the propellant surface coming due to the heat transfer from the flame with this one, which is the heat absorbed by the propellant for temperature rise and decomposition and pyrolysis of the fuel. We can simply write kg Tf minus Ts by x star is going to be equal to m dot C into Ts minus Ti plus delta H V and what about our m dot? M dot we have said that m dot is the rate of vapor release from unit surface area of the propellant. Now, if we consider this the mass burning rate of the propellant per unit area, we can simply write that m dot is going to be equal to the propellant density into R, where R is the linear burn rate. R is the linear burn rate. So, this vapor is coming due to the regression of the propellant. So, as the propellant surface is regressing over time, if we consider the linear regression of the propellant is R, which is in let us say millimeter per second or centimeter per second, some length regression. So, if we consider the linear regression of the propellant is r, we can denote this m dot, which is rate of vapor released per unit surface area of the propellant. We can relate this with this equation. If we replace m dot in terms of rho p into r, we can easily get a relationship with r. So, we can now simply put this in terms of r. So, this will become C into T s minus T I plus delta H V. So, what we can write here, we can simply write the equation for r will become k g into T f minus T s by x star divided by rho p into C into T s minus T I plus delta H v. So, this equation suggests us that if we have increase in flame temperature, so T f is the flame temperature. The increase of flame temperature is going to give increase or give rise to the burn rate, and that is quite true also, because if the flame temperature is higher, we expect like more heat transfer from the flame to the propellant surface. So, increase in flame temperature will in turn cause increase in burn rate. If we have increase in the initial temperature of the propellant, that will also going to improve the burn rate of the propellant. If we lower down the x star, if we decrease the value of x star, that will in turn is going to help increase in burn rate. So, increase in flame temperature will also going to improve the burn rate. The decrease in x star is going to increase in burn rate. Increase in T I is also going to increase in burn rate. So, there are various influencing factor which is going to influence of the burn rate, but the reaction rate is going to be very much dependent on the pressure, as we have seen in case of the double base propellant. If we relate the standoff distance with the reaction rate of the propellants, we may find out that the pressure has a major effect on the reaction rate, and that will reduce the flame standoff distance. So, as we have higher reaction rate, the flame standoff distance is going to decrease as we increase the pressure, because the pressure has a influencing role on the reaction rate, and that will decrease the standoff distance. So, therefore, in turn we can say that R would very much depend on pressure. So, in the similar line we can say that the burn rate or linear burn rate of composite propellant is also going to be expressed as in burn rate law A R equal to A p to the power n, what we have seen in the previous occasions for double base propellant, where n is the pressure index which is bringing the effect of pressure, and A is taking care of the other things like the initial temperature of the propellant, the composition of the propellant, the physical nature of the propellant, that will be taken care of by A. Now, we can say that size and pressure have very influential role on the size of size, means we are talking about the size of ammonium perchlorate crystals. Pressure, type of binders, catalyst, so many things. I mean, these are not just only parameters, but there are many other parameters which are going to influence the burn rate of composite propellant. So, if we try to get the value of A and N, what we need to do is we have to perform experiment with a constant pressure. We keep on changing the pressure, at different pressure we have to generate the value of, we have to get the data for burn rate, and from the curve fitting we can actually find out the value of A and the value of N. Okay. So, in a similar way the pressure index N and A can be determined from the experimental values. The pressure of interest in solid propellant rocket typically ranges. So, the chamber pressure in solid rocket generally ranges from 3 to 15 MPa, which is like 30 to 150 atmospheric pressure. And as you have already mentioned that at this pressure the diffusion flame dominates the overall combustion process. So, diffusion flame dominates the combustion process of composite propellant, because at high pressure we have already discussed that at high pressure the reaction rate will be quite high, whereas the diffusion or the mixing of oxidizing species and fuel species will not up to the mark compared to the reaction rate. That is why the diffusion flame will be the dominant here in case of this pressure range. Now, our job is to see that what are the different factors which is going to influence the burn rate of composite solid propellant. Now, we can see that at low pressure the pressure exponent, the value of N is generally in the value around 0.5 or so, because there actually APPF dominates at low pressure, and at high pressure the value of N is in the order of around 0.3 to 0.4, generally beyond ten atmospheric pressure. So, the value of N is in the order of like 0.3 to 0.4, whereas in double base propellant we have seen that the value of N is generally in the higher side, about 0.6, 0.65, 0.56 like that. So, at low pressure since APPF dominates, the value in the range of 0.5. However, these values will depend on different ingredients of the propellants. So, if we just want to bring about the effect of the pressure, we need to conduct the experiment, mainly the strand burning experiment is conducted, and the value of A and N are determined, and we can actually get this thing from the curve fitting of the data. Now, looking at thickness of the reaction zone, we have already said that. Looking at the pressure, if we see the different type of propellants here, it has been compared with like double base propellant also and some AP based composite modified double base. It is not directly composite propellant here, it is like AP based some composite modified double base, but still we can see the effect of pressure with the burn, the effect of burn rate, the burn rate influenced by the change of chamber pressure. So, we can see as the pressure is increasing, the burning rate is going to be increased continuously, like we can see for double base propellant it is here, but for composite propellant you can see as the AP percentage increases, the burn rate is also going to be increased. We can see this here, and as the pressure is increasing from 10 atmosphere, 20 atmosphere, 50 atmosphere, the burn rate is also increasing. Okay. So, in both case either double base propellant or composite propellant, pressure has an influence and role on the burning rate of the propellant. So, as we have seen in case of double base propellant that it is a strong function of pressure, similarly for the composite propellant as well, it is also a strong function of pressure. Now, what are the other effects which is going to influence the burn rate of the propellant, we have to look at carefully. One such example is the effect of AP particle size. We have already discussed in the discussion of during the discussion of the combustion mechanism of composite propellant involving ammonium perchlorate crystals. We have said that as the ammonium perchlorate crystal sizes reduces, the standoff distance is going to drop, or the flame tries to come closer to the propellant surface. I mean to say that as the particle sizes of the propellants decreases, if this is the propellant surface, the flame is somewhere over here. So, we are considering this flame as a single plane where where all three flames are there. So, the flame standoff distance is going to reduce as the particle sizes become smaller. So, from the experiments also it has been observed. Now, these two plots are showing for two different two different combinations. One is for bimodal case. Bimodal means for efficient in packing, to improve the packing density, the ammonium perchlorate crystals are packed into different sizes, bigger and smaller, so that the smaller crystal can take up the void space created by the bigger particles due to the arrangement of the bigger particles. So, the bimodal cases, the mixture of bigger crystal or the larger crystal and smaller crystals are used. So, if you see here for bimodal case, as the particle sizes decreasing from combination from 350 to 200 micrometer bimodal. So, it is like 4:1 ratio it has been used. So, 350 and 200, here you see it is like 15 to 15 micron and 3 micron combination. Here also 4:3 ratio the mixture has been prepared for the crystals. For the pressure effect, we can see that it is increasing. In both cases burning rate is increasing with pressure, but for the bigger crystal we can see the burn rate is lower compared to the smaller crystal. Here the crystal size is like 15 micron and 3 micron combination, whereas this one is like 350 and 200 micron. So, we can see the burn rate is going to increase as we make the epicrystal lower. In both the cases, the oxygen to fuel ratio is maintained at 80:20 AP by HTBB ratio. So, for a same oxygen to fuel ratio, while decreasing the size of the crystal, the burning rate is increasing. Now, if you consider the same thing for monomodal case, means only one type of crystal sizes used in the propellant combination, there also we can see as the pressure is increasing, the burn rate is increasing. So, there is no difference in that, but as we decrease the particle size, the burn rate is actually increasing. So, we can see that this is the 265 micron sizes, whereas this one is 55. There is some discrepancy in the data, like this one is also increasing, this one is the 55. So, we are supposed to have like this one. So, maybe some discrepancy, but overall we can say that as the crystal size of the ammonium perchlorate decreases, the standoff distance decreases and eventually the burn rate is going to increase. So, the pressure and the particle size has an influence and role on increasing the burn rate if we increase the pressure and if we decrease the particle size. Now, in the next lecture we will try to see what are the other effects which are also going to control the burn rate of composite propellant. For example, like type of binder, what are the different polymeric binder we used, is there any influencing role on the burning rate of the propellant because of the change in binder, or the percentage of binder, like if we decrease or increase the binder binder percentage in the propellant matrix, whether there is any change in the burn rate. Similarly, there are other effects like catalyst. Now, catalyst can be like positive catalyst or negative catalyst, means the catalyst can either increase the burn rate or it can decrease the burn rate. So, based on the choice of the catalyst, there is an influencing effect on the burn rate of the propellant. So, in the subsequent lecture, I think we will try to explore on the effect of those parameters. All right, thank you.